Today is November 29th, 2024. I will talk about from orthogonality to least square method, the flow. First, in this chapter, the most important thing is orthogonal basis for the subspace W of Rn and orthogonal set of non-zero vectors in Rn. This is the keyword. If orthogonal set, then it will be orthogonal basis. So actually, these two sentences are sentences that represent same things as others. If I read it, if S equals to U1 to UP is an orthogonal set of non-zero vectors in Rn, or orthogonal basis for a subspace W of Rn, then S is linearly independent and basis for subspace spanned by S. And this is the proof. If some linear combination is zero, then we can write it as 0 dot U1 equals to like this, then it will be C1 U1 dot U1. And so if it is orthogonally diagonalizable, then you can write Y dot U1 as C1 U1 plus CP UP dot U1 or C1 U1 dot U1. Please try to prove it. And let's say, again, there are orthogonal bases, then you can write Y, which is some vector. You can write it as linear combination. You can then decompose it with G1, which is in the subspace, and G2, which is in the W complement. So we will feed the notion of orthogonal complement with orthogonal projection, which is if we say there is vector U in Rn, we can write it as Y equals to Y hat plus G, and Y hat is projection on Y of vector Y. We will write it as Y dot U dot U, Y dot U over U dot U multiply U, and Y hat, of course, we can represent it as scalar alpha multiply U, and we should find, then we can change the problem as finding alpha to make Y minus Y hat orthogonal to U. We can write it as Y hat dot G equals to G, dot product is 0. We will then see, we discuss about orthogonal set. We will make a hierarchy from independent set to orthogonal set and orthonormal set. Independent set will be some set that becomes basis, two vectors which has some angles not perfectly correlated or perfectly negatively correlated, then it will be independent set. It can be orthogonal set if the two bases, angle between two bases is 90 degree, or it will be pi over 2 cosine pi over 2, then it will be 0. So cosine theta equals to 0 is very important. In orthonormal set, the angle is 90 degree and its vector's length is 1, then we will say orthonormal set. So we will solve a very simple example. This is the orthonormal basis of a plane in R3. We will check if it is orthonormal. First, check each vector's dot product is 0, which means the angle is 0. You can check by having dot product. Dot product can be also U1 transpose multiply V2. V2 you can use easy one, and you should also check about the length of vector is 1. By definition, it will be calculated by square root square of each element sum, and you don't need to square root because the answer should be 1. All right, and we will also talk about orthogonal set of unit vectors property, which is U has orthonormal column if and only if U transpose multiply U equals to identity matrix. Has 3 property. First property is X is arbitrary vector, then the length should be same between U multiply arbitrary vector and arbitrary vector. Second thing is U multiply X dot U multiply Y should be same with X dot Y, and it should be 0 if and only if X dot Y, X dot product Y equals to 0. We can say the property of A and C as linear mapping from X to UX preserves the length and orthogonality, because even you do multiply U, the length is same, and even you do multiply U, the orthogonality is same when X dot Y equals to 0. So we can say this linear transformation preserves orthogonality. You can also write it as ut dot u as matrix multiplication. Then you can find out this result. Okay. So when you do orthogonal projection, you will write y hat as y project onto each of vector u, and z is orthogonal to every vector in w, and also orthogonal to every basis vector in w. Both will be true or false. And now we'll see the notion of orthogonal decomposition. Before that, orthogonal projection, we will go more deeper understanding the orthogonal projection, which is the orthogonal projection of a point in R2 onto a line through the origin has an important analog in Rn, which is given a vector y and a subspace w in Rn. There is a vector in y hat in w. Y hat is a unique vector in W, which is closest to Y. Think about Y as dot, then Y hat is the closest one from dot. And also, Y minus Y hat is orthogonal to W. We can write it as Y minus Y hat dot Y hat equals to 0, or Y minus Y hat that W equals to 0. This is a little bit confused. And there will be property, which is if you want to use P be an orthogonal basis for W, and if Y happens to in W, then the formula for project Ly is project Wy. If Y in W, which is 10, you want to use P, then project Wy will be Y, because Y is in subspace W. And we will see orthogonal decomposition, which is let W be a subspace of Rn, then each Y hat in Rn can be Y equals to Y hat plus J, which is Y hat is in G and G is in W complement. Then any orthogonal basis of W, you can write Y hat as each of orthogonal projection. This is the notion of orthogonal decomposition. You can also prove it that y hat is in W and G is element of W complement. Let's say it is orthogonal basis. You can define y hat as linear combination of basis of U1 to UP. Then you can define G, which is y minus y hat. Since UI is orthogonal, U1 is orthogonal to UP, G dot U1 equals to 0, then you can induce it. G is orthogonal to U1 and it's Uj in the basis for W. G is orthogonal to every vector in W. So G is in WT. W complement. And also you can prove the uniqueness by just assume there is another y1 plus g1. Then y minus y1 will be g minus g1. And you can prove it. It's actually same. Yeah. In this case, there is u1 and u2 and there is y. Y hat will be y that is projected to u1 and u2, the sum of two. And this is Bayes approximation theorem, which is let W be a subspace for Rn, let Y be on any vector in Rn, let Y hat be the orthogonal projection of Y onto W. Then Y hat is the closest point. We can write it as length of Y minus Y hat is smaller than Y minus 3 for all 3 in W is from Y hat. And it does not depend on the particular orthogonal base used to compute it. We can draw a picture to prove it. We can use Pythagorean theorem. You can solve the distance from y to span u1 and u2. You can find y hat, which will be orthogonal wait a minute, which will be from y to project to each. Then after that, you can find using y equals to y hat plus g. You can minus y hat. So you can simplify it. And this is another theorem, which is project W, y project onto W will be this because it's orthonormal basis. What is divided by U1, the product U1 will be just length will be 1, so it will be gone. And then you can calculate this as U multiply UT multiply Y, which if you write it as metric form, there will be vector U1 to UP and U1 to row U1 to UP and Y. Then you can write it as U1 dot Y. Then you can calculate it as U1 dot Y, Y dot U1, A1 by metric representation. The Gram-Schmidt method is very simple. We talk about basis and orthogonal basis and orthonormal basis, like just 2 or 3 slides ago. We want to make basis as orthogonal basis, even basis is not basis. How can we do it? First, if there's V1 to VP, we will say first vector is just Z1, but from the second vector, we will make it as orthogonal to first one, which is second vector minus with this orthogonal. It looks like we see a lot in orthogonal projection, which is will be that is V2, and you make orthogonal projection to V1. So if we summarize Gram-Schmidt method, it is for VP, find projection of XP onto V1 to VP minus 1 and remove the projection from XP is what Gram-Schmidt method do. And this is the now this is least square problem. Least square problem is like the intersection between linear algebra and statistics. How it can be connection between both of two. It's very simple. Let's say consistent and inconsistent notion. There will be only one or many solution if it is consistent. If not, we will say it is not consistent. This should be a very simple example. If there is only which is 1ax plus y plus bx form of equation is exist. And if we make it as matrix form, it will be y, and there is a matrix, and there is alpha beta. In this situation, there is 2 unknown variables with 4 constraints. If we write it in a equation format, then alpha and beta can solve every 4 equation, usually. Then in this situation, we should use least square method, which is there will be B, which is not in AX. Just make projection of B onto column A. So we will find approximated solution, which is B minus AX hat is smaller or same than B minus AX, length of B minus AX for all X in Rn. This is the least squares notion. And if we transform the equation, then we can get A transpose multiply AX equals to A transpose B. If we can solve it to get the solution, which is called by normal equation. How can we induce it? Which is AX hat is orthogonal to B minus AX hat, and AX hat is linear combination of column vectors of A, and B minus AX hat, we can represent it as vectors. If we just rewrite it algebraically, and we can also see the geometrical solution, which is when only column of A are orthogonal, or maybe we can make it by orthogonal Gram-Schmidt, then there will be A1 and A2 which is orthogonal. Then we can find B hat as B projection to A1 and B2, B projection to A2. The sum of those, then we can find geometrical solution using orthogonal projection. And there is some property, which is those following are equals, which is AX equals to B has a unique least square solution for each B in Rn, which equal with the columns of A are linearly independent, and A transpose A is invertible. This is because the part of normal equation, when you found it, you should move A transpose A part to right side as having inverse sign, and normal equation has a unique solution. It's the same thing. Next time we will talk about, it will be chapter 7.1 based in Ray's linear algebra. We will talk about symmetric metrics and the relationship of orthogonally diagonalizable, and metrics what is only orthogonal or only invertible, and matrix which is A square is zero matrix. Then in that case, is it diagonalizable? Or if diagonalizable, what will be the eigenvalue? We will talk about it next time, and we will solve more problems that we discussed before here. Each of the problems. What is h of b? How does it affect to the number of solution? And b has the only one solution. This case, this kind of case, and projections, and this matrix multiplication part using matrix representation, row perspective, and column perspective. We will, by using this, we will solve the problems. Problems. Okay. Orthonormal matrix with property and these things. Most important thing here, the proposition will be orthogonal basis for a subspace W of Rn, and also orthogonal set of non-zero vectors in Rn will be the one of the most important thing. Thank you very much today.